Welcome to example number 6. In a 1901 circus performance, Allo Daredevil Diavolo introduced the stunt of riding a bicycle in a loop-the-loop. And the radius is given of 2.7 meters, and we want to know what is the least speed v that Diavolo has to maintain at the top of the loop in order to not lose contact at the top of the loop-the-loop. So, and this example can be used in several different situations. A lot of vertical circles, like for example, a roller coaster would be the same real setup. So, what we're going to do first is we're going to draw a free body diagram for Diavolo and his bicycle. We're going to assume that there are just really one particle here. So let me go ahead and draw a little picture of him here. So if we look at Diavolo here and his bicycle, we could draw a free body diagram, and we'll note that there are two forces really acting on him. There is the force of gravity due to the earth pulling him and his bicycle downwards, and there is also a surface force, a normal force coming from the top surface pushing downwards. So that's this top of the loop-to-loop. Now there are other forces that are acting tangentially here. For example, there would be a frictional force pushing it forward and also a drag force pushing it backwards, but they are not contributing to any radially inward acceleration towards the center of the circle, which is down here. So there is a centripetal net force going downwards towards the center of the circle, so there's a acceleration towards that center here. So if we were to apply Newton's second law, sum of the forces equals mac along the y-axis, and we'll just choose in this particular case to make the y-axis positive downwards because all our forces are down and our net force is downwards. So the two forces that would be contributing to that net inward force would be the normal force plus the force of gravity, which is equal to mass times the centripetal acceleration, which is mv squared over r, and r being the radius of the circle. Now at the top of the loop, the track exerts a normal force on the bicycle as long as the bicycle is moving with a speed great enough to stay on the track. If the bicycle moves too slowly, then it starts to lose contact with the track, and then the normal force becomes zero. And so we're looking for that limiting situation where it starts to lose contact with the surface here. Basically, if it starts to lose contact, then there is no normal force. So we're going to assume that the normal force is approximately equal to 0 to find that minimum speed. So mg equals m, and we'll just call this v minimum squared all over r. And we'll see that the mass cancels out here, and we get the minimum velocity is equal to the square root of g times r. Now remember that we're looking for the situation where the normal force must be greater than or equal to 0, so really the velocity basically must be greater than or equal to square root of gr. So at least equal to that at minimum, and anything bigger will create a normal force and it'll be fine. So therefore, the normal force is now, or the minimum velocity now, is going to be square root of 9.8 meters per second squared times the radius of the loop, which is 2.7 meters, square root of that whole thing, which gives you about 5.1 meters per second. And you can convert that to kilometers per hour, and that's approximately 18.4 kilometers per hour. So he has to maintain at least a speed of 18 kilometers, 18.4 kilometers per hour to go around that loop-de-loop. Now in reality, he's probably going faster than that. Otherwise, he would fall away from the track and then he would make the complete circle around here. This same type of example can be applied to other examples that are very similar. For example, it could be a roller coaster and you're looking for the situation where people start to fall out of their seats. So you would look for that minimum velocity so that people don't fall out of their seats in a roller coaster situation. Or you could have just a pendulum bob, a little string, and it's basically being whirled around a circle, and you're looking for the situation where the tension becomes 0 and it could just barely make a circle here. So they're very similar situations and solved the same way. And that's it for example number 6.